Let us now talk about the normal distribution. Height or weight of human beings are continuous variables. I'm sure you can think about many other continuous variables. That means that if measured accurately enough, they can take any value. Therefore, it makes little sense to ask questions like, what is the probability that someone chosen at random has height exactly 194.3 centimeters? The mathematical answer is clearly 0. However, it is perfectly legitimate to ask questions like, what is the probability that someone chosen at random has height between 194.25 centimeters and 194.35 centimeters? Or what is the probability that someone chosen at random is taller than 194 centimeters, has height greater than 194 centimeters? When the variable is continuous, we are concerned with a range of values rather than a single value. Like many other naturally occurring continuous variables, the height of adult men can be modeled by a normal distribution. I'm sure you have seen it before. This distribution has a distinctive bell-shaped curve and is symmetrical about its middle. The curve is obviously continuous, the variable is continuous, the curve is continuous. And the following figure, next page, probability is represented by area. So the shaded area to the right of 194.3 centimeters represents the probability that a random selected adult male is over 194.3 centimeters tall. I've said shaded area, it's the green area in the picture. This is the color. So the area right to the 194.3 centimeters. The shaded area, the green area, can be calculated by using the function phi of z. You will be given tables when you are attending your exam. The function phi of z gives the area under the normal distribution curve to the left of the value z. The total area under the curve is obviously 1, is normalized, and the area given by phi of z represents the probability of a value smaller than z. If the normal variable x has mean mu and variance sigma squared, then x, a particular value of capital X, is transformed into z by the equation z equals x minus mu divided by sigma. Z is a particular value of the variable capital Z, which has mean 0 and variance 1, and is the standardized form of the normal variable, the one given by the tables you'll be using during your exam. Please notice that capital X and capital Z represent the normal variable in itself, while small x and small z are just particular realizations, particular values of these variables. So, if the mean of x is mu, the mean of z is 0. If the variance of x is sigma squared, the variance of z is 1. For a particular value x, z equals x minus mu divided by sigma, as we've said. This is a particularly important example. Assuming the height of adult man is normally distributed, which it is, with mu, the mean, equals 174 centimeters and sigma, the standard deviation, equals 7 centimeters, find the probability that a randomly selected adult man is A. Under 185 centimeters, B. Over 185 centimeters, C. Over 180 centimeters, D. Between 180 centimeters and 185 centimeters, E. Shorter than 170 centimeters. Let's discuss it. The mean height is 174 centimeters. Mu is the mean. The standard deviation is sigma equals 7 centimeters. So we find that if x is 185 centimeters, z is x minus mu divided by sigma. So 185 minus 174 divided by 7, which gives 1.571. Phi of 1.571 equals 0.9419, which is equal to 0.94 to two significant figures. So, the probability that an adult man chosen at random is under 185 centimeters is 0.94. The probability that an adult man selected at random is over 180 centimeters is obviously the probability of the complementary event of the previous case, so the complement of the previous probability. So P over 185 centimeters is obviously 1 minus P under 185 centimeters. So it's 1 minus 0.9419, which equals 0.0581, which is equal to 0.058, always to two significant figures. The probability that a randomly chosen adult man is over 180 centimeters is the same, can be calculated with the same procedure. X equals 180 centimeters. So Z is 180 minus 174 divided by 7. I haven't put a unit of measure to Z because it's centimeters divided by centimeters, obviously, which gives 0.857. Phi of 0.857 is 0.8042. You find the values of phi, let me repeat it, on the tables. So 1 minus phi 0.857 is 1 minus 0.8042 equals 0.1958, which can be approximated to two significant figures as 0.20. The probability that randomly chosen adult man is between 180 centimeters and 185 centimeters is nothing but the difference between the phi of Z equals 1.571 and phi of Z equals 0.857, which, so if we put numbers, is 0.9419 minus 0.8042, which equals 0.1377, which is 0.14. Let's now tackle an important case, the probability that an adult man selected at random is under 170 centimeters. If X is 170 centimeters, Z is 170 minus 174 divided by 7, which gives minus 0.571. Tables do not give negative values of Z. However, the normal curve is symmetric. We've said it before, symmetrical about its middle. So the area to the left of Z equals minus 0.571 is the same as the area to the right of Z equals plus 0.571. That's to say, phi of minus 0.571 equals 1 minus phi 0.571, which is 1 minus 0.716, which gives 0.284, 0.28 to two significant figures. The probability that an adult man chosen at random is under 170 centimeters is P equals 0.28. Some of you sent me an exercise about fish. The text said, the lengths of fish of a certain type have a normal distribution with mean 38 centimeters. It is found that 5% of the fish are longer than 50 centimeters. There were three questions. A. Find the standard deviation. B. When fish are chosen for sale, those shorter than 30 centimeters are rejected. Find the proportion of fish rejected. C. 9 fish are chosen at random. Find the probability that at least one of them is longer than 50 centimeters. Let's see. If mu, the mean, is equals 38 centimeters, the value of Z corresponding to X equals 50 centimeters is clearly Z equals 50 minus 38 divided by sigma, so 12 divided by sigma, the standard deviation. To calculate sigma, that's the question, we make use of the information that 5% of the fish are longer than 50 centimeters. What does it mean, 5%? It means that the area to the right of 50 centimeters is 0.05, 5 divided by 100. So 1 minus phi of Z, we don't have Z, because we know that just the Z is 12 divided by sigma, is 0.05. Therefore, phi of that particular value of z must be 0.95. From the tables, we find that the z which corresponds to phi equals 0.95 is z equals 1.64. If z equals 1.64, that means that sigma equals 12 divided by 1.64, which is 7.32. So we have found the standard deviation. The standard deviation is sigma equals 7.32. Now let's discuss the solution to points 3 and 4. The point 3 is analogous to a man being under 170 centimeters. Remember from the previous example, we want to know how many fish are shorter than 30 centimeters. So z is 30 minus 38, which is the mean, divided by 7.32, which is the standard deviation we've just found it, which gives minus 1.09. Phi of minus 1.09 equals 1 minus phi of plus 1.09, which is 1 minus 0.8599 equals 0.1401, which gives 0.14. So 0.14 is 14%, 14 divided by 100. So 14% of the fish are rejected because they are shorter than 30 centimeters. 13% of the fish are shorter than 30 centimeters. From point 1 now above, we know that 95% of the fish are shorter than 50 centimeters. So the probability of 9 randomly selected fish to be all shorter than 50 centimeters is just 0.95 to the 9th, because each individual fish has a 95% probability of being shorter than 50%. So now we have 9 individual fish, so p equals 0.95 to the 9th, which is 0.663. So the probability of at least one fish, not one, but at least one fish to be longer than 50 centimeters is just the probability of the complementary event. So the complementary probability, which is 1 minus 0.6302, which gives 0.3698, 0.37. I hope that's all clear. However, we will be discussing it tomorrow during class. Thank you.